Hello again, and welcome to the next installment of the final exam review for Calculus 3208. And we're still looking at limits and continuity, but this, I believe, is, yes, the last section on limits and continuity. So our installment number 15 now. We're going to look at oblique asymptotes that we can find by looking at what we call the almost limit of rational functions that sometimes occurs. So let's get down to the nuts and bolts here. We've got, first of all, 3 points we want to raise in this session. One is, how do we do long and synthetic division of polynomials? That's a topic that's also covered in your Math 3200 course, but it's very useful for us when we're finding oblique asymptotes. So we'll go through that quickly. And then we're going to look at what's called unlimited but predictable behavior. So oblique asymptotes are kind of a funny thing. They're an asymptote that is neither vertical nor horizontal. They're kind of slanted. Some folks even call them slant asymptotes, but we call them oblique. And we're going to look at how we find the equation of an oblique asymptote from a rational function and its equation. All right, so let's get started. First of all, if we look at the expression that's given as an example here, we've got x squared minus 2x minus 3 over x plus 2. If we try to divide that out the easy way, and the easy way is if we can take that expression, if we can take that expression and if there's some way we can factor it like this, so it'd be x minus 3 times x plus 1 all over x plus 2, and we can't really make that divide easily because there's nothing to cancel out, so we're going to have to divide it the hard way. So that's all there is to it. So what we do is, let's just get this out of the way and look at what sort of techniques we have to employ here. So the first method is long division. Long division is really helpful. If you're going to find the oblique asymptote, or if you're going to have to use division of polynomials, and your divisor is not a linear term like this one, x plus 2, then long division is really helpful. We don't use it very often, so I'm just going to do one example of long division here just to run us through it. So what we do is we look at the x plus 2 that we're trying to divide into x squared minus 2x minus 3. So I ask myself questions when I do this. So the first question is, what would I need to multiply x by to give me x squared? And of course the answer to that is x. So I've got an x there, and so I take this x and I'm going to have to now multiply it by both the x and the 2 that I have over there. So I'm going to get x squared plus 2x. And I write those two things down here when I multiply them by the x that I chose. Then we use subtraction just like we do with long division of numbers. So I have negative 2x, subtract positive 2x is negative 4x here. And of course, x squared minus x squared will give us a 0, so I don't need to worry about that. That'll always work out okay because we chose this value of x up here to make it work. Then we take the last number that we have and we pull it down here with our negative 4x. So it's the same mechanics as long division that you learned in elementary school. And then what we're going to do is we're going to ask ourselves another question now. What do I need to multiply x by to give me negative 4x? Well, that's a simple question with a simple answer. How about negative 4? So then we're going to have minus 4x minus 8, and then we subtract negative 3, subtract negative 8 is negative 3 plus 8, giving us a remainder of 5. Okay, now we're going to look at another method to do the same thing. So what we just found out is that when we divide these two, we get x minus 4 with a remainder of 5. Synthetic division, how does that work? Well, I take the factor x plus 2, and I think, well, if that factor did give us a root for this equation, then the root would be negative 2. So we've got to change that sign. Then we simply write down the coefficients of the polynomial that we have in the numerator, 1, negative 2, and negative 3. And then it's algorithmic. We start with the 1, and we simply drop that straight down here. And the thing that folks typically like about synthetic division as opposed to long division is that it's addition and multiplication instead of division and subtraction. So we take negative 2 times this 1. So we take our negative 2 multiplied by this 1, and that gives us negative 2. And then we add negative 2 plus negative 2, negative 4. And then I have negative 2 times negative 4, giving me 8, positive 8. And then we add again, negative 3 plus 8 is a remainder of 5. Okay, so what we find out here is that our answer is, since we have a quadratic divided by a linear, we've got two coefficients, so it's x minus 4 with that remainder. Same thing we got when we did it by long division. So how do we write this out correctly? Well, when I take this rational expression and I divide them, I got an answer of x minus 4, but I did have this remainder of 5, so I say plus 5 over the original divisor, which was x plus 2. So basically we can say that these two expressions are equal at all values of x, except of course where x equals negative 2, because at that point they're both going to be undefined. So those two expressions are always equal except at that non-permissible value. All right, so that's how we do our division of polynomials. Now let's see if we can talk about what happens to a function like the one we just saw. So this one right over here, what's going to happen to this function right here? We rewrite it this way, and we're going to talk about its behavior as x goes way off to positive infinity. Okay, well, we know that the degree of the numerator is greater than the degree of the denominator. So we know from our previous work that there's not going to be a horizontal asymptote, so this limit actually would be at infinity. So as x approaches infinity, y approaches infinity because this function doesn't have any limits. However, we notice that this degree is 2 and this degree is 1, and that's the special case that we have to worry about for finding an oblique asymptote. It's only going to be possible if the degree of the numerator minus the degree of the denominator is actually equal to just 1. So the numerator has to have a greater degree, but only one more. So here we've got 2 minus 1 is 1, so we're good. So this one's going to work. So then what we do is we look at this new way that we wrote out that expression over here to see if it's going to give us any good information about this. Well, as x approaches infinity, let's look at all of this stuff together. And specifically, this last little bit that had to do with the remainder that we found. If I look at that remainder, for very large values of x, when I get closer and closer to infinity, this business is going to be less and less significant because 5 divided by larger and larger numbers here is going to approach or get very close to 0. So for larger and larger values of x, the original function that we started off with here is going to be more like the x minus 4, and this business is going to count less and less. So what we say is that as x approaches infinity, the expression that we had is going to get really close to just x minus 4. So what that tells us is that for large values of x, this function approaches x minus 4. Okay? So what does that mean? Well, x minus 4 is a diagonal line. We know how to graph a linear function, and basically it tells us that when x gets really, really big or close to infinity, then the graph of this function should get closer and closer to this particular line. And that means it's going to approach it as if it were an asymptote, except it's a diagonal asymptote, sometimes called slant, mostly called oblique. Alrighty, let's look at these examples that we have here. The first one just says to divide some polynomials. So let's use synthetic division, nice and quick because we have all linear divisors, so that makes it easy. So we'll take a positive 1, and then we're going to divide that into this quadratic, and its coefficients are 3, minus 5, and plus 1. So we start by taking the 3 and dropping it directly down here and then multiplying. Then we add those two together. So I multiplied, the 1 by the 3 to get this one. Adding these two gives me negative 2. Multiplying 1 times negative 2 is another negative 2. And then adding those two gives us negative 1. So that's our remainder. And we have this expression is going to be equal to 3x minus 2. Our remainder is negative 1, so we can say subtract, because it's negative 1, 1 over x minus 1. So if I were to draw a graph of this function, we'd anticipate an oblique asymptote at 3x minus 2, because this part will become less and less significant. All right, so for the last one here, now notice this one's a bit of a funny monkey. We've got to divide x plus 3 into 7x squared plus 1. So I'm going to turn the x plus 3 into a minus 3 as if it were a potential root, and let's see what happens. Now, you'll notice that this is a quadratic numerator, but there's no term with an x in it. There's no linear term here. So what we do is we say that this is 7x squared, 0x, and then positive 1. So we have to put the 0 in there to make sure our placeholders all end up in the right place. So we drop the 7, multiply by the negative 3, add those together, multiply by negative 3 again, 63 we have here. Adding that stuff up gives us a 64. So we have a huge remainder here of 64. And basically, when I divide all these things out, I end up with 7x minus 21 plus my remainder of 64 all over x plus 3. But again, if we're talking about the graph of this, which is where we're headed with this stuff, this will be the oblique asymptote, and this stuff over here will be relatively insignificant for large values of x. All right, we mosey on. Here's our second example. It says find the equation of the oblique asymptote for this. So basically the same idea. We'll take -1 as our potential root, which we know is not really a root here. We're going to take 5, 3, and 1 as our coefficients. And we're going to drop the 5 and multiply by the -1. Then, or sorry, just drop the 5, multiply by the -1 to give us a -5 here. Then we add those together. Then we multiply by -1 again to give us a +2. Add those together, and we get a 3 for our remainder. So one more time. Drop the 5, multiply it by the -1 to get here. Add them together to get there. Multiply by the -1 again. Add those up, and there's your remainder. So this expression is equal to 5x minus 2 plus the remainder of 3 over x plus 1. We know that for large values of x, this isn't going to account for very much. So this graph will approach this line. So we have our oblique asymptote at y equals 5x minus 2. That's a nice linear function. Next, test type question. Which function has an oblique asymptote? So if you were paying attention, you will remember that there's a condition that we have to get an oblique asymptote. The degree of the numerator has to be just 1 greater than the degree of the denominator. So 2 of these are not like the others. Look at these guys. No way. The denominators are bigger. That's no good because we've got quadratic denominators, linear numerators. Not going to do it. Let's look up here now. This one looks like a good potential candidate, and so does this one at first glance, but until we see this. Aha! So the x minus 2's divide out. So here we have f of x is actually exactly equal to x plus 7, except at our non-permissible value of 2. So this one doesn't have an oblique asymptote. It is a linear function, just with a point discontinuity. There's our oblique asymptote. So the first one, A, is our only option. We move along. Find the equation of the oblique asymptote for y equals x squared plus 1 divided by x minus 2. So one more example of the same old business. We're going to take 2 as our potential root, divide it on into 1 as a coefficient of x squared. We have a 0 as our coefficient of x, and a 1 as our as our constant term on the end. Drop the 1, multiply by 2, add them up, multiply again, add them up again. There's our remainder. So this function is equal to x plus 2 plus we've got 5 over x minus 2 is our remainder. Oblique asymptote, this stuff is not going to matter when x gets big, so we've just got y equals x plus 2. Nice, simple, linear function. Alrighty. So here's the your turn question for this section. Determine the equation of the oblique asymptote for this function. So notice that this is cubic over quadratic, but with a few little tricks and pranks, you're going to be able to get away from that pretty quickly and turn it into something that's a little easier to work with. And if you want to work on that now, go ahead, pause the video, do what you got to do. I'm going to show you the solution. Your turn solution is given here. So all the gory details that you would need, and your oblique asymptote turns out to be at y equals x plus 1. All right, let's summarize what we've talked about. So key ideas we've had for any rational function when the degree of the numerator minus the degree of the denominator is 1, and at least one factor of the denominator does not so-called cancel, then the function will have an oblique asymptote. Okay? So it's really important to keep all of those things in mind. The difference between the degrees has to be 1, and you can't cancel out all your factors in the denominator. Otherwise, you're just going to have some function that's not even really rational. It's just got some point discontinuity or point discontinuities on it. Next, it says to find the equation of the oblique asymptote, we simply divide the numerator by the denominator, just like we did with both synthetic and long division. And the remainder that we get for that will approach 0 for large values of x, so that remainder is insignificant, and the quotient gives the equation of our oblique asymptote. All right, hope that helps. If you have any questions, don't hesitate to post them on D2L. Hope everybody's having a good time studying. I know I'm having a good time helping. See ya.